Human heights follow a bell curve. So do measurement errors, exam scores, the daily variation in your commute, and the weight of loaves from the same bakery. These things have nothing in common. Different causes, different units, completely different mechanisms. So why do they all end up the same shape? There's a real answer, and it isn't that nature likes bell curves. It's that the bell curve is what happens when you add up lots of small independent things. Today, we generate normal data. Check the famous 68, 95, 99.7 rule by counting rather than trusting it. Learn the one number that tells you how unusual any value is, and then spend the back half on the much more important question of when assuming a bell curve will actively cost you money. The normal distribution has exactly two parameters, which is part of why it's so convenient. Mu, the mean, says where the center sits. Sigma, the standard deviation, says how spread out it is. That's it. Two numbers fully describe the entire shape, forever, at every point. Almost no other distribution is that cheap to specify, and that cheapness is a large part of why it's the default assumption everywhere. But here's what people take from that and shouldn't. Because the shape is determined by the mean and the standard deviation, it's tempting to think that reporting a mean and a standard deviation describes your data. It only does if your data is actually normal. If it isn't, those two numbers can be a summary of something that looks nothing like the thing you're imagining, and everything you conclude from them will be confidently wrong. Generating it is one call. Random.normal with a mean, a standard deviation, and a size. Let's do adult heights. A mean of 170 centimeters, a standard deviation of 10, 100,000 people. Number PY hands us back an array of 100,000 heights drawn from that distribution. The single most useful operation on normal data is standardizing it. Subtract the mean, divide by the standard deviation. That converts any value into a z-score, which is just how many standard deviations from the middle it sits. A height of 190 centimeters becomes a z of 2, and here's why it matters. A z-score means the same thing regardless of what you measured, so it lets you compare a height to an exam score to a delivery time. Now let's check the rule instead of quoting it. We count what fraction of our 100,000 people fall within one standard deviation of the mean, then 2, then 3. 68.3%. 95.4%, 99.7%. That's the famous rule, and we didn't look it up, we measured it. Here's what that looks like. The histogram is our simulated heights. The curve over it is the theoretical density, and they sit on top of each other because the simulation is drawing from exactly that shape. Now let's shade beyond 2 standard deviations. That amber region is everything unusual, and it's about 4.5% of the area, split between both ends. Push further out, and the numbers get severe fast. 2 sigma is 1 person in 20. 3 sigma is 1 in 370. 4 sigma is 1 in 16,000. 5 sigma is 1 in 1.7 million. Each extra step is not a bit rarer. It's roughly 20 to 50 times rarer than the one before. The tail falls away exponentially, and that is precisely where the trouble starts. So here's how to use this properly. Use a z-score to compare things measured on different scales. Use the 68-95 rule for quick sanity checks. And before you assume normality, plot a histogram, because it takes 10 seconds and it catches almost every case where the assumption would have burned you. If the shape has 2 humps or a long tail on one side, stop because the tools that follow all assume it doesn't. Now, the caveat, and it's the whole reason this episode exists. The normal distribution says a 5 sigma event happens once in 1.7 million. Financial markets produce moves that large every few years. Not because the maths is wrong, but because returns aren't normal, they have heavy tails, and the normal curve assigns almost zero probability to exactly the events that matter most. Every major risk model failure of the last 40 years is some version of this. We'll come back to it in episode 12. One sentence. The bell curve isn't a law of nature. It's what averaging does to lots of small independent effects. And when those conditions don't hold, neither does the curve. Which raises the obvious question. Why does averaging do that? Why should adding up unrelated things produce this one specific shape? Next episode, the strangest result in statistics.